Hello, good morning. My name is Jake McGregor, and I'm here to talk to you a bit about Minerva Intelligence and some of the work that we've been doing for Natural Resources Canada over the past year or so. So let me just get my screen up here. I hope you've been enjoying the first morning here at GeoIgnite. And so over the past year, we've done a couple different projects. One we've just wrapped up and one we're doing right now. Both involve hydrology. The first was a project called NFHDL, the National Flood Hazard Data Layer. And I'm going to get into that a bit more today. And the other one that we're working on is we are redesigning or designing a new schema for the NHN, the National Hydro Network dataset. So both are really exciting projects, and I'm going to tell you a bit more about those today, and kind of get into why Minerva Intelligence is working on these projects. So first, let me show you a bit of the flood data that we have in Canada. So this first map is a one layer from a flood data set from the town of Happy Valley, Goose Bay. Gotta love that name, in Newfoundland and Labrador. And this was a study that was just finished last summer in July of 2020. And when you download the data set, there are two geodatabases, each with 8 features within them. And each one of those features is essentially just one polygon showing a flood inundation area that's been modeled under different scenarios. And you can see that each one of these layers that we're looking at has some of them have been modeled under open water conditions. Some of them have been under ice affected conditions. So that means that there's been like an ice jam that's been incorporated into the modeling. Some of them have been done with a 100-year return flood or a 1% AEP. That's an annual exodus probability. And some of them are done with a 20-year. And then you'll see at the end, there's a code that says CLC or CC. CLC means climate change conditions. So that means they're taking into account the rising sea level and changes in precipitation. And then the CC indicates that it's under the current conditions. So really all the information that we know about each one of these layers, if we are to just download these flood maps from the GeoPortal from Newfoundland and Labrador, is the information that's contained within these titles, the names of each one of these features. So that's just one example in Labrador. But now if we take a look at Ontario, something very different. So this is the Grand River Conservation Authority, what they provide in terms of a flood map. And this is what is called a regulatory floodplain. And so you can see that this isn't one river or even one study. They've basically taken an amalgamation of all sorts of different studies, compiled it into one shapefile for you to download. And then fortunately, it's quite well documented and there's some attributes. But as you can see, this is quite different than the type of flood map that we were looking at in Newfoundland and Labrador. And I'm just going to give one more example, and this is what we have in Quebec, which is actually a provincial scale database. And now this called the BDZI is going to be soon to be replaced by a more current, but it is still the authoritative flood data source in Quebec. And it's a well-structured, although old database that has different polygonal and linear representation of different features. There's relationships between them. And one interesting thing to point out about the BDZI is that the study area is represented as a linear feature along the river that was studied. So in Alberta, in most areas where we have a study area feature, it's a polygonal representation that encompasses either as a bounding box or some sort of buffer, or where the study actually took place around the features. Whereas in Quebec, they represent it as a linear feature. So really all of this is just to say that there is a lot of different types of flood hazard data and flood mapping techniques and ways of representing the end data all across Canada. And really for me as a geographer, what's interesting is the data structure and the way that people who might not have a ton of expertise in geospatial data actually store this data for users within a geospatial environment. So the project that we did, we started by collecting data all across Canada, all these different flood maps, some of the ones that I've shown you today, and a lot more. And then we engaged with all the provinces and territories to kind of learn more about how they store their data and what they're doing with it, how they're doing modeling, what their future plans are for flood mapping. And then we took to designing a schema. That was an iterative process where we got feedback from stakeholders as well as Natural Resources Canada. And once that had been completed, we took all the data that we collected, transformed it, put it into one cohesive format. And then we also developed a prototype which is essentially a tool that enables NRCan or people who are maintaining the National Flood Hazard Database to input new flood maps as they come to be adherent to the schema. So yeah, I think that you can see that really the main purpose of this project was to create data interoperability, and so that emergency managers and government can really look at flood mapping in one coherent format. The way that we have it right now, it's really hard to compare a flood map like the one we saw in Happy Valley to something that we have in Ontario or BC. They're all just represented so differently, even though fundamentally they're an area that's been modeled to show where a flood is going to go. So at a fundamental level, they're the same thing, but they're being represented in so many different ways. So really, the thing that we were trying to accomplish is interoperability of these flood maps. And when I talk about interoperability, I'm really talking about three different things. The first thing is the geometry. And I think that this is becoming less and less important, as we have systems that can project on the fly, but really this is making sure that, and I mean, for flood mapping, it is important because, very small changes in geometric errors can result in a building being impacted by a modeled flood or not. So making sure that the geometry and the coordinate reference system, the projections, all of that is interoperable, and that can all be compared within the same system. The next part of interoperability, which I think is probably the one that we all think about the most, is the data structure. So that's what features are there, and what are the relationships between these different features, as well as what attributes the features and tables in the data structure have. I think the third and sometimes forgotten component of interoperability is the semantics. So that's the terms that we use to describe the features, as well as the terms that we use to fill different attributes of those features. So a lot of times we think of these as code lists, or they're stated as specific code lists. And these code lists can be hierarchical or they can be flat lists. What we're looking at here is an excerpt of some of the code lists from the Canadian Wetland Inventory Project that is being led by Ducks Unlimited Canada. They have a very good set of code lists describing different parts of wetlands and also classifying wetlands into different types. So yeah, I mean, for the NFHDL project, and I think really any database design project or anything that's involving interoperability, you have to, of at least spatial data, you have to consider all three components of this. You have to consider the geometry, you have to consider the data structure, and those are the ones that we often think about and consider. But the words that we use to describe the data, the semantics of it all, is really important. And sometimes we kind of assume that people are going to know what is being said, but we really have to make sure that those semantics are well thought out and that we're explicit, so that we have documentation stating what we mean by every term that's being used within our spatial data. So, for example, in terms of flooding, I think it's really important to understand that, you know, if we have something that's listed as coastal flooding, there's lots of different things that could be, but primarily it's either a coastal storm or storm surge, and a tsunami. And these would be things that are being modeled completely differently. And if we don't state which type of modeling was done or what type of flood hazard was being assessed, there's going to be hugely different implications for how an end user of the flood data is going to be, you know, looking at that in terms of preparing a community, determining where or where not people should build, all of those types of considerations. Then the reason that we create these maps kind of hinges on the words that we use to describe them. And I think that this is something that's often overlooked in flood data, especially since these types of flood studies often hinge so much on a very dense report. And that's where all the information about the modeling, where the study area was, what data was used as input, all of that information is kind of housed in the study report, but it kind of gets forgotten that a lot of times that report gets separated from the end data, and someone is just looking at a line that has, you know, an annual accidents probability on it on a coast, and they don't know whether that's, you know, for a coastal storm or whether that's like something that's been modeled as a recurring earthquake event that's going to cause a tsunami. So making sure that we're using our words as much as we can and making sure that we're explicit about the definitions is really, really important. So Minerva is really, you know, we're an AI company. I don't even think I've introduced us, but we're an AI company based out of Vancouver. And semantics is something that's really, really important to us. We use semantics all throughout our process. And I'm going to talk a little bit more about kind of how our AI technology works. And I think that'll help you understand how it is that an AI company from Vancouver got into the place of designing national databases. So just to help you understand how our technology works, I want you to take an example. And I use this example all the time because I really think that pretty much everyone can relate to and can understand it. And this isn't an application that we've built, but I want you to kind of think about this, and I think it'll help you understand how Minerva's AI technology works. So imagine you're going out and you're trying to buy a new apartment or rent a new apartment. You're going to kind of have a bunch of different things that you're thinking about. What price is appropriate to you? Maybe let's say you absolutely need at least 2 bedrooms, but you kind of want 3 bedrooms. You're going to build out all these different requirements. Maybe you don't care if it's close to a school, but it really needs to have a balcony. All these types of things. We're going to kind of specify different properties of what your ideal apartment looks like. And that's really what we've done, is we've created a conceptual model, that we've encoded it in a graph format describing what your ideal apartment is. And we use that conceptual model, we just call that a model, to compare against all the listings that we have in our apartment listing database. And we're going to compare your model to those listings to see which ones are the best matched. And by doing so, by comparing that one model, that conceptual model, to a whole bunch of different listings out there of real places, we're going to be able to present to you what is the best match for your apartment search. One of the best things that we can do about this that a traditional SQL type query wouldn't be able to do is that we can provide non-exact matches. So even if we don't have something in some of the results, it's still going to come up because we're using kind of a more qualitative approach. And you can see that the terms in the data here, even in this kind of toy example, are already becoming really, really relevant. So you see in that best match that we've matched a balcony to a veranda, and that's because the taxonomy underlying this application would understand that a veranda is a type of balcony, and we'd still be able to award the points there. So like I said, this is just an example. Some of the real things that we do is build applications in both mining and natural hazards or climate adaptation solutions. So what you're seeing here is an excerpt from one of the maps that we've produced in the Sea to Sky area. It's kind of a proof of concept project for our landslides application. And in this application, we use conceptual models that describe different landslide types and how those landslides occur. So we have conceptual models for debris flows, soil slides, rock slides. And by comparing those to descriptions of the landscape, we can identify areas that are at most risk of different landslide types. So each of these polygons that we're seeing on the map is a hillside that has been encoded with all sorts of different information. And what's important here, to tie back to some of the work that we're doing for NRCan, is that we have to make sure that we're using standardized language so that all of our conceptual models describing landslides are using the same vocabularies as the data that we use to describe the locations. So that's how our landslides application works. But we also have an application in mining, and that's kind of what we were founded on. And we use our technology in a bunch of different ways, but one of our applications is called Target, and it compares conceptual models of mineral deposit types. So there's different types of gold deposits, different types of copper deposits, uranium deposits, and they all have different attributes that are commonly found in those deposits. So what type of rock, how far it is from different types of faults, what elements are enhanced there, what elements are depleted there. And we can compare mineral geochemical samples to those conceptual models and try to identify areas that might be prospective for finding new mineral deposits. Okay, so that's Target. And now I hope that you can see that really a lot of what we do is focused on structuring data and structuring knowledge to make it more useful within practical solutions. And really, we like to consider what we do as knowledge engineering. We're structuring data and human expertise in such a way that it can be used and reused for practical applications and for making predictions. So knowledge engineering is really about getting that human expertise and encoding it so that it can be used in a computer system or an AI application. And that human expertise can be about how a mineral deposit is formed or what causes a landslide to occur, but it could also be all sorts of things like what causes a specific disease or your expert opinion of why you think that a specific apartment is best for you. So a lot of these applications that we've built are spatial, but really our technology doesn't have to be used in that function at all. And that's really where we're moving now, is we're trying to make the tools that we've used to build these applications more accessible to developers and to solution creators. And so you can take our knowledge capture tool to ingest domain expertise, and then you can use Solus to help align and standardize terminology to the same vocabularies that you use to capture your knowledge. And the reasoner is kind of our AI engine that compares the knowledge models captured through knowledge capture and the data that's been standardized through Solus in order to create similarity scores and explanations for all the results. That's something that we really tried to drive home, is that everything that we do is completely explainable. And I think that in the geospatial domain, as we get more and more satellite data, more and more IoT sensors, we kind of forget, and we're trying to move away from terminology and describe everything in numbers. And we kind of expect machine learning or statistics to make use of those numbers, but look at us, we're still here, we're still communicating through words. And really that's my one takeaway message from this presentation, is that words are really important and we use them in our data, so don't be afraid to use them and be thoughtful when you are using them. So thank you very much. My name is Jake McGregor and I'm the Chief Operating Officer at Minerva Intelligence. Thank you very much. Have a good day.
Oh, awesome. Thanks a lot, Jake. That was a really, really informative presentation. And, we always think about the industries and the technologies of the future, and AI is absolutely one of them. So it's great to see the application of AI in geosciences and to learn so much from what you had to share with us. To all the attendees, I think you're all informed of our Q&A spot. You can post your questions. So I think just in the interest of time, Jake, I'll just go straight into some questions from the audience because we already have a few very interesting ones here. And maybe I'll start out here with one of the questions I see from Farah Hoke. The question is, in terms of semantic matching by synonyms, i.e. veranda versus balcony, and I like the example you gave in picking an apartment, what procedures do you implement to match two results? Do you have a data dictionary? That's the question.
Yeah, I'm happy to answer that, David. So our system, our reasoner, as we call it, our cognitive AI engine, is built on terminologies, and it really relies on ontology to link all the knowledge and all the different words that we're using to store information about our data. And so an ontology really just links the concepts between words in a specific domain. And often that's linking different taxonomies together. And so taxonomy is often hierarchical, like that example of the balcony and a veranda. And we build these taxonomies. There's lots of different tools out there, but Minerva has a specific tool called the ACE, which is an open access tool that you can find online. It's called ACE at minervaintelligence.com. And that tool allows us to specify the different properties about different terms in a domain. So you would describe what a veranda is, and the system would understand that because of the properties of a veranda, it is a subtype of a balcony, and that our system can reason with those properties and understand that when we have a balcony, it's related to a veranda, and award the points for our matching applications.
Okay. Cool. Yeah, so I have another question here from Christopher. What is your vision in the development of AI and geospatial technology? And will AI and automation replace an image analyst and a GIS analyst in the positions of the future?
That's a great question, and one that we kind of get a lot. And I think that our perspective, at least on AI and the types of tools that we're building, is to provide intelligence amplification or intelligence augmentation. And that's really kind of the a bit of an older school perspective on AI as a decision support tool. So that's something that can help our experts and really just be another tool in their tool belt to help them solve the problems. And that's really why we focus so much on explainability in our results. So that means that every prediction that we make and every result that we have, so every landslide model compared to a landslide like instance on a hill, is explained in natural language, because we know that the experts who are using these systems need to have defensible results, ones that they can explain. And if they're going to shut down a highway or close a development of a housing community, they need to be able to explain why they're doing that. And a lot of machine learning applications are kind of black box and don't provide that explainability. So that really ties back to, giving the experts in these fields the tools to make decisions in the best way that they can, and be able to explain why they're making those decisions.
Yeah, cool. Yeah, and I think you touched on a really good part of that answer with the concept and the issue of defensibility of the results of any work that includes artificial intelligence and machine learning and such. There's a good question here from Roberto Figueroa that maybe ties to that a little bit. In your presentation about interoperability, Roberto asks, shouldn't accuracy also be a part of the interoperability? And, for instance, follow-up part to his question is, there are significant differences between regulatory mapping, and I think it ties back to your point about defensibility of the results.
I mean, when it applies to flood mapping in particular, it's definitely really important that accuracy is interoperable, and I think the way to do that in that domain is just to make sure that information is available to the user, so they know at what scale the modeling was done and the mapping was done, because the accuracy, when we have different flood maps that are being created at different scales across the country for all sorts of different studies, like Canada has so many different types of floods, like I was talking about on the coast, but we also have riverine floodings, and all of these maps are produced at different scales and with different accuracies. So just making sure that information is available to the user is the best way that we can create interoperability, because the maps just aren't going to be produced with the same accuracy when we're talking about a country the scale of Canada.
And that's a really good point. And when you touch on that and leading to, for example, the national floodplain work that you did, who are some of the other key stakeholders involved? And this is a question from one of our participants here, Canadian GIS, and is asking, who are some of the key stakeholders who are involved?
So when we were developing that project, the key stakeholders that were involved with the development of the schema were primarily the provincial and territorial authorities. So that's the water management departments or natural hazards departments, emergency managers at a provincial scale. But I think this product in the end is something that is going to be have stakeholders all the way down to every single one of us. Like, all of us have who own a house or live in an area that's either on a coast or near a river. Like, really, that makes us all stakeholders in making sure that this data is available and interoperable. Even if we're not the ones using it, we're the ones who live with that risk, especially as climate change is making these hazards more and more imminent.
Yeah, absolutely. And I think even just going back to your example about choosing an apartment, you'd like to know if it's in a flood zone or not. And one of the questions I think I had was, when will this national flood hazard data be available? Will it be available there, publicly available? And how would it be made available? Because obviously there are so many different applications and opportunities for application development in real estate, insurance, and other risk management spaces. You can comment on that.
Yeah, thanks, David. I think that's an important question to ask, and I think there's lots of people from NRCan and from the government here. So I think that's really a question that comes down to them. It's not something that I can answer directly. Right now, our task was to build that data set and provide it to NRCan. What happens next is up to them. And I guess I also think that it's important that that data set is available to all of Canada. Yeah.
Okay, cool. Oh, that's great. We only have, well, we already passed our time, so I'll, there's a whole pile of questions here, and I think as we learned from the morning session, there's a lot of interest in this talk, and I'm not sure if you're on our Slack channel where maybe some of these questions can be answered and made available to more people. But I think I'll just take one last question from the chats that I thought was very interesting. It was tied to the earlier question about the AI and how you match the knowledge, but many ontologies already exist for a variety of domains. And do you incorporate existing ontologies, and are there challenges in standardizing them? This is a question from Nate Currit, and I think that will be our last question, given how many questions we have and how much time we have.
That's a great final question. Like I said, we're huge proponents of interoperability and standardization. We're members of the OGC. I sit on an ISO committee, and we want to make use of any previous work that's been done and leverage existing standards and existing work. So whenever we're going into a new domain, we always take a look at what ontologies or knowledge structures, because there's a lot of ways to take UML structures and convert them into ontologies. And so we always take a look at what's existing. A lot of times we find issues or small errors in those, and then we try to fix those. But really working off existing work is something that's very, very important to us.
Oh yeah, build on what works and is known, and lead us into the future of AI and geoscience. Thank you so much for that talk, Jake. It was really informative, and clearly a lot of curiosity from our audience. And thank you very much for your time.